Okay, so today we're going to work through an example of finding the acid dissociation constant, or Ka. So what I have already written up here is our general form for finding Ka, and it's going to be Ka equals our hydrogen ion concentration times our anion concentration over the concentration of our acid. And that would be for our basic dissociation of an acid that we have here. And if you notice, this looks very, very similar to what we did last chapter when we found KEQ. And it's going to be, again, similar where we're finding concentrations at equilibrium to find Ka of a weak acid. So that's what we use if we have just a general acid. But in our example, we know what acid we have, so it'll get a little bit more specific. So our example, we have a 0.1000 molar solution of ethanoic acid has a hydrogen ion concentration of 1.34 times 10 to the third molar, 10 to the negative third molar. And then we're going to calculate Ka for that acid. So we have ethanoic acid, which is CH3COOH. So I'm going to write out what that's going to look like if it dissociates. So I'm always forming hydrogen ion. And if I take a hydrogen away from that, I'm left with let's try and write that a little better. CH3COO minus. So that's going to be the more specific version of that equation right there. So when I look in my problem and look at what I know, it tells me my concentration of ethanoic acid, so that's my CH3, let's write that as an actual 3, COOH, is 0.1000 molar. We also know the concentration of our hydrogen ions, which is 1.34 times 10 to the negative third molar. Again, like last chapter, if we have hydrogen here and we have this ion, they're both products, they're being produced at the same rate, they have the same coefficient, so their concentrations at equilibrium have to be the same. So our concentration of that CH3 COO minus is also going to be 1.34 times 10 to the negative third molar. And we are trying to find Ka. Now, it might seem like we have all the numbers we need right now, but we actually have to do one more thing. Because the numbers we have, this first number is our initial concentration of our ethanoic acid, where these two are our equilibrium concentrations. And we need the equilibrium concentration of everything. So to find that equilibrium concentration of our ethanoic acid, it's actually very simple. So as that reactant is being converted into our product, everything up here, all of our coefficients are 1. So it's all at a 1-to-1 ratio. So to find our equilibrium concentration, we just take our initial concentration and we just subtract whatever our concentration of hydrogen ions that we formed. So we subtract 1.34 times 10 to the negative third, and that is going to end up giving us 0.0987 molar. So now that is our equilibrium concentration of ethanoic acid. So that's the number that we're going to actually want to use in our problem. So now I'm going to go back up to this expression and I'm going to write what that's going to look like for this specific example. So to find Ka, we want our concentration of hydrogen times the concentration of, we had CH3COO minus, and that's all going to be over a concentration of ethanoic acid, CH3COOH. So we can plug in our numbers then. Our concentration of hydrogen ions is 1.34 times 10 to the negative third. Our concentration of that ion is exactly the same, so we're going to end up squaring this, save myself some room. And we're going to put that over the concentration, equilibrium concentration of our ethanoic acid, which is 0.0987. And when you do that on your calculator, and you get 3 sig figs, because 1.34 times 10 to the negative third molar has 3 sig figs, you should get 1.82 times 10 to the negative 6. Oops, I lied. You should get 1.82 times 10 to the negative 5th. Okay? And just like our equilibrium constant, our KEQ from last chapter, Ka does not have a unit, so we are done.